Hi everyone, here we are with chapter 14, and chapter 14 is on chemical periodicity. So we're going to be talking about certain trends in the periodic table, and we're also going to be talking about categories based on their electron configurations. So let's go back and review the periodic table first. So if you remember, Mendeleev was the first person to organize the periodic table successfully, and he organized the periodic table based on increasing atomic mass. Okay, but later we discovered that that probably wasn't the best way, because the way that he had the periodic table organized, it had some of these holes and gaps in the groups and stuff. So it wasn't the best way. So now our periodic table is organized in terms of increasing atomic number. Okay, so that is really, really important. So what does that atomic number tell us again? It tells us the number of protons. So that is how our periodic table is organized, based on increasing atomic number, not atomic mass. And as we are getting into second semester stuff, chapter 13 was on the electrons, where the electrons were located. And the reason why we're so concerned about the electrons is because the electron plays the most important role in terms of chemical and physical properties of a particular element. Okay, so between the proton, the neutron, and the electrons, it is the electron that has the most important role. So that's why we're trying to figure out where these electrons are located. Now, there are four categories that we can arrange or organize the periodic table based on their electron configurations. So the first category, okay, so this category number one, are your noble gases. So if you remember, your noble gases are on the right-hand side of the periodic table. They are the very last group, right? So we call that group 0 or group 8, and we say that these gases are inert. Do you remember what inert means? Inert means very low reactivity. Basically, they don't react very much at all because they are stable. So very low reactivity. And based on their electron configurations, your noble gases have their outermost S and P sublevels completely filled. So when we say outermost, that means their last energy level, okay? Their outermost energy level, where the S and P's are completely filled, meaning they have 2 electrons in each orbital. All right, so that's category 1. Category 2, so this is number 2, are your representative elements. So the representative elements, based on their electron configurations, are categorized based on S or P sublevel is only partially filled. Okay, so that means that at the end, they may not necessarily have 2 electrons on each line. Okay, your representative elements are also known as the main block elements. All right, so here are some examples of representative elements, and remember, some of the groups have special names. All right, so group 1, alkali metals, group 2, alkaline earth metals, and remember, group 7 also has a special name, halogens. Okay, halogens. And so these are basically groups 1 through 7. Sometimes some periodic tables might include group 8 in terms of representative, but mostly groups 1 through 7. And your representative elements, there's this term called valence electrons. Now, valence is the number of electrons in the outermost energy level. So once again, outermost energy level is the very last energy level. And there's a really fast, easy way that we can determine how many valence electrons an atom has. We can just look at the group number. So this is important to know. The group number equals the number of electrons in the outermost energy level. So that is the quick and easy way. So for an example, group 1 will have 1 valence electron. Group 2 will have 2 valence electrons, so on and so on. Group 3 will have 3 valence electrons. So here we have an example, lithium, sodium, and potassium. And when we look at potassium and sodium and lithium, all of these elements are found in which group? group 1, right? They're all found in group 1. So if we take a look at their outermost energy level, we can see that S1, 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 right? So 2S1, 3S1, 4S1. Those are all of their outermost energy levels, right? And they only have one electron in the outermost energy level, which corresponds to their group number, right? So that's just how you can see how the valence electrons are equal to their group number. Okay, let's go on to categories 3 and 4. So category 3, these are your transition metals, okay? Transition metals. So transition metals, you know where they are located. That's where you start to fill the D sublevel, right? So it says outermost S sublevel and nearby D sublevel contain electrons. And then your fourth group are the inner transition metals. So the inner transition metals are where the outermost S sublevel and nearby F sublevel generally contain electrons. So those are the two rows that are thrown down at the bottom of your periodic table. Now let's take a look at those categories where they're located on your periodic table. So remember, category number 1, noble gases are right here, okay? So your noble gases are where the S and P sublevels are filled. Then we have category number 2 called the representative elements. So these are your representative elements, and these are the ones where your S and P's are partially filled. And then we have your transition metals. This is where your S sublevel and nearby D sublevel contain electrons. And your very last category are these two rows at the bottom of your periodic table. So those are called the inner transition metals. So they're called the inner transition metals because these two periods are actually inserted right there. So that's where you start to fill the F's, okay? That's where you start to fill the F's. All right, so now we're going to shift to something new. Now we're going to go into the periodic trends. So there are 3 main periodic trends that we are going to talk about. The first periodic trend we are going to talk about is atomic size, which is also known as atomic radii. So let me explain to you why we refer to the size as radii. Radii is plural for radius. Remember, your atoms are in, their electrons or whatever, are in these electron clouds. So remember, clouds have fuzzy boundaries. They do not have like a definite boundary, right? A cloud. So they take 2 atoms, put them side by side, okay? Yes, they should be even, and they are not even. Here's the nucleus, here's the nucleus. So since the clouds have fuzzy boundaries, they have to stick 2 atoms together, and they measure the distance from here, from nuclei to nuclei. So you can see radius, radius, so plural, radii. And that's how they measure the size of the atoms, okay? So you need to know these trends. So the trend for size, notice here that size, as you go down the periodic table, it increases. It gets bigger in size, okay? The atoms will typically get bigger in size. And then as you move across the periodic table, the size of the atom is going to get smaller, okay? Smaller. Now, these are just trends to help us understand, like generally this is what happens to the size of the atom, but you know, there always could be exceptions to the rule. So not only do you need to understand the trend, to know the trend, you need to understand why. Why does it get bigger when you go down? Why does it get smaller as you move across? So that is what we're going to talk about first, okay? So let's talk about why it gets bigger going down, all right? So when you're going down the periodic table, so let's just make some notes here. So let's just write this down here. Okay, so it gets bigger in size as you go down because you are adding on energy levels, right? Adding energy levels. And besides adding on energy levels, well, so that means you're adding on rings, right? So yes, it is going to get bigger as you're going down the periodic table. So not only are you adding on energy levels, there is this concept called the shielding effect. Okay, shielding effect. So what do shields do? They block, right? They block or they protect. So let me explain to you the shielding effect. Let's see where I can draw a picture. All right, so imagine that we have a nucleus. Let me draw this small. All right, so here's a nucleus. The nucleus is positive. The first energy level, the second energy level, the third energy level. So let's assume that I'm going to do an analogy to a concert. So right here, the nucleus is the stage. Okay, the nucleus is the stage. We can only fit 2 electrons in the first energy level. We can fit 8 in the second energy level. So 1, 2, 3, 4, 5, 6, 7, 8. And then I'm just going to put 1 electron in the third energy level. All right, so let's pretend that the nucleus here, this is the stage. You're at a concert, all right? Obviously, if you have front row seats or you're in the first energy level, you're going to be really attracted to the nucleus, right? You're going to be really attracted to that concert and really drawn in. But then look at the people in the second row. You know, these electrons in front of them are kind of blocking or shielding their view. And then you take a look at this poor guy over here. All right, this electron, he's got like really bad seats. He's like way out there. And all these other electrons, all these electrons here are shielding or blocking his view from the concert. So he's not as drawn in, okay? He's not as drawn in. So he's going to hang out a little bit larger, right? So that's why it gets bigger in size, because he's not as drawn in or attracted to the nucleus. He's just going to hang out a little bit wider, all right? Because he can't see. And eventually what's going to happen, maybe he'll just take off and leave the concert because he's not as attracted or drawn in because everyone is blocking his view. Okay, so that is the shielding effect. And the shielding effect, you need to know this, going down the periodic table, okay, the shielding effect increases also going down. So I'm going to use white here. So shielding effect increases as you go down the periodic table. Okay, now let's talk about why the size of the atom gets smaller as you move across. So if you're looking in one particular row, one particular period, you'll notice that, for example, the second energy level, second row, as you're moving across the periodic table, all right, so as you're moving across the periodic table, for example, the second row, you're adding on protons every time, right? The number increases, you're adding on protons, which means you have a stronger nuclear charge. All right, so let's write that down. Stronger nucleus charge, stronger nuclear charge. Therefore, it's going to pull in all of those electrons in tighter. So that's why they get smaller in size, okay? It's really pulling in all the electrons towards the nucleus because that charge is very strong, so they're very attracted. So that's why it gets bigger in size, smaller in size, okay, as you move across. So the size of the atom could help you understand its attraction to the nucleus. So the smaller it is in size, the stronger the attraction to the nucleus. The larger it is in size, the less attracted the electrons, the outer electrons are to the nucleus, okay? So this is what it kind of looks like. Okay, it's just a trend. So generally, you can see what happens as you go across. Notice these are getting smaller in size. Once again, nuclear charge is increasing, so they're being pulled in tighter. Going down the group, notice they're getting much larger, okay? Because you're adding on energy levels, but not only are you adding on energy levels, the shielding effect is being increased, okay? You got more and more inner electrons blocking the nucleus so that the outer electrons are not as attracted. So they're just kind of hanging out and they get larger in size. Something that I forgot to notice or mention about the shielding effect as you move across the periodic table, the shielding effect actually remains constant as you're moving across, okay? The shielding effect will only increase going down. All right, we're just going to review some of your ionic charges because we're also going to talk about ionic size. So you have your anions over here. Remember, anions have a negative charge, and they get the negative charge by gaining electrons. Then you have your ones over here and some over here that have a positive charge, and most of your metals here too all have positive charges. Those are called cations, and they get that positive charge by losing electrons. All right, so that's important to remember. Now, as we're talking about ionic size, the trend is the same as atomic size, okay? The trend is the same. So if you're comparing all anions or if you're comparing all cations, going down the periodic table, the size will increase. As you're moving across the periodic table, it will decrease, it gets smaller. So it's the same trend as atomic size. Now, let's take a look at the next picture, and you can actually see what happens to cations and anions and how their size changes from their neutral atom. All right, first thing I want you to do is let's take a look at this side here, okay? Notice this column shows you the size of the atoms, and we're going to be comparing the neutral atom to the cation. What do you notice happens to the size as it turns into a cation? So as it turns into a cation, it gets smaller in size. Okay, so these are smaller in size. And I like to, think of your electrons like weight. So lose electrons, losing weight, they're going to get smaller in size, right? And the reason why they get smaller in size is because since they are losing electrons, okay, they're losing negative charges, that means the nucleus is getting stronger because now you have more protons, okay? You have more protons than electrons, so everything gets pulled in tighter. So lose electrons, lose weight, all right? And you get smaller in size. Once again, the smaller it gets in size, that means it's getting more and more attracted to the nucleus. Now let's take a look at the anions. Look what happens. As they gain electrons, they're getting bigger in size, okay? Remember, anions are gaining electrons, so they are like gaining weight. They are getting bigger in size. So these ones are getting larger. So now they have more electrons than they have protons, so it's not going to be as drawn in to the nucleus, okay? All right, our next trend is ionization energy. You need to know the definition for ionization energy. It is the energy required to remove an electron, okay? The energy required to remove an electron. So this one is going to die going down. So let me explain to you what die represents. Die represents decreasing ionization energy. Okay, die. So for ionization energy, it decreases going down, dies, because like when somebody dies, they go down and get buried into the ground. So that's how I kind of remember it, all right? So if it's decreasing going down, then therefore it must increase going across. So this one is an inverse relationship to the size, right? Because remember, it's getting bigger in size as you go down. Remember, if it's bigger in size, those outer electrons are not as attracted to the nucleus. So they're going to hang out a little more, and then therefore the outer electron is going to be much easier to remove because it's not as attracted to the nucleus. Whereas as you move across the periodic table, it's very small in size, which means it's very attracted to the nucleus. It's going to be a lot harder to remove that outer electron. It doesn't want to leave. Okay, because it's very drawn in to the nucleus, very attracted to the nucleus. All right, so ionization energy is the opposite of size. Your very last trend is electronegativity. Once again, you should know the definition. All right, you should know the definition. It's when the atom is able to attract electrons to itself. Okay, so you need to remember that fluorine is the most electronegative element. If you remember anything in chemistry, remember that fluorine is the most electronegative. This is like a very common question, like in chemistry, like which atom is the most electronegative? Well, fluorine is. So that means that if fluorine is the most electronegative, then you know it's going to increase towards fluorine and then therefore decrease going down. So let's think about it. On this side of the periodic table are your anions, the ones that form negative charges. So they want to gain electrons, right? They want to gain electrons to be stable like one of the noble gases. So these over here on this side have a high attraction for electrons. Whereas these ones over here, which are your cations, they rather lose electrons than gain electrons. Okay? So electronegativity and ionization energy have the same trend, and then size is the opposite, okay? Now here's the table of electronegativity values. Okay, this is like their attraction for electrons. Now, which group of elements is missing from this table? You should notice that it is group 8, right? Group 8 would be over here, which are your noble gases. So now let's think about that. Why would your noble gases not be on this chart for electronegativity? Well, let's think about it. Do they want to attract electrons, or do they need to attract electrons to themselves? No, they don't. They already have their S and P's completely filled. They are already stable. So they don't need to attract any electrons at all. All right? So as you can see here, yes, once again, fluorine, right? Most electronegative. And then these are the smallest ones on that side. And that is everything that you need to know for chapter 14. It is very conceptual, okay? So you need to, practice doing problems and understanding the trends. And make sure you understand the trends, like why they get smaller, why they get larger, why do they lose electrons easily, why is it more difficult, so on and so on. All right? Okay, I'll see you guys later. Bye.